everybody. So yes, I'm Michael Hush, Chief Scientist at Australia's first venture capital funded quantum technology company. So what is that? WTF, what is quantum? I'm here to tell you a bit about what the big push is to create these new quantum technologies, quantum computers in particular, why there's so much investment, why people are really working hard to make it happen, why it's hard, and why you should think about it and how it could impact your future. So there are many ways in which quantum technology is defined. Much of it is annoyingly technical, and I'm not going to give you that, but the simplest way to think about it is we're looking to build a new set of technologies which use our understanding of the physics on the smallest level. So the science that we've discovered around how atoms act, how extremely cold gases act, we're using that information to build a set of new technologies. And these technologies are going to have huge impacts from everything from the way we develop chemicals to the way we move around the world, how logistics and operations are optimized, and how you can be brought from one location to another more safely. So it's been estimated with all of these potential applications that there's a $850 billion worldwide market, and there's a huge push around the world to make this happen. So at Q-CTRL, we started working on this 6 years ago. No, 7. 7, I sometimes forget how long I've been doing this. So we were founded by Professor Michael Biersick out of the University of Sydney. And we've started with a group of 4 of us. And we initially were really working on improving the performance of quantum computers. But as the technology got better, as it's improved, and as we started expanding into other quantum technologies like quantum sensing, we found ourselves thinking less about how do we get these things to work and more about how are they going to make an impact in the world. And so Q-CTRL's purpose now is not just making technologies work, but really helping everyone understand what they're going to do and then getting them in your hands and making them create a difference for you. So to achieve that, we've really had to think globally. In fact, in the first year of operating, we first opened our US office, and we've since opened offices across the UK and the EU as well. There's 140 staff of us, and just to give you an idea of our size relative to the other companies in the world, we just closed our Series B this year, and that was for $133 million, which is the largest Series B that's ever been raised by a quantum software company. So the software and the technology that we're building, we've worked hard to build it, and we've worked with a variety of partners, which has led to some great customers who trust the work that we're doing. So we have over 20,000 actual daily software users who are using the software we're developing. We work with a variety of different hardware partners, and we work with some of the best in terms of government. We work closely with the Australian government and the Australian Defence Force, along with a great representation of some really big innovators on the commercial side, like IBM and SoftBank. We do 2 things. So we do quantum computing, but we also do this thing called quantum sensing, where we use similar concepts and control techniques to very sensitively detect the world around us. But today I'm going to talk about quantum computing, because I think it's in some ways the most WTF. So I wanted to give everyone a bit of a taste of, a clearer picture of what's going on in that space. If you want to talk about quantum sensing, I'm more than happy to just contact me through the app, and I'll have a chat about it. So when I was preparing for this, often people just get straight into quantum computers are great, you want one. But I just really wanted to revisit, like, why do we want to get more and more compute? Because these days, like, everyone has a phone that can get you access to all the information you could possibly want, and also all the possible videos you would want. It feels like compute is now ubiquitous, and it's at a level where it can get you what you want immediately. But there are still really important things that we're trying to do and understand, which are limited by our ability to compute, how fast our computers are and how effective they are. I'm just trying to put like the very simplest example, which is predicting the weather. So this isn't a plot, of course it's a plot because I'm a scientist by background, so there's only going to be 2 bits of data in here, but please forgive me for presenting them. You can see that over the last 20 years, our ability to predict the weather over 3 days, we started pretty well, but we got a lot better recently, where we're almost at 100%, down to around 10 days ahead on average, where we're remarkably bad in the 80s, and we've got almost up to 40% now. There's still a big gap there. But you can see that we're getting better at actually being able to forecast the future. And so some of this is to do with us having some more sensors, but really the thing that's improved our ability to predict the weather has been better compute. It's bigger computers, more computers, able to process information faster. So that's really this concept that I want to get across, is that we're really trying to make better computers to better predict the world around us so that we can then be more efficient, be more safe, make better decisions so that we achieve what we're trying to achieve. And you can see, even in this simple example and our common day-to-day experience, there's still a lot more work to do. We are not great at predicting the future. Even 10 days out when it comes to a weather forecast is extremely hard still. The last other driver, which, look, it's a bit more controversial, so I'm not going to talk about it too much, but like the other big driver that's going on right now, which I'm sure you're all aware of, is the push for artificial intelligence. And that is an application which is so hungry for compute, it's consuming and pushing the need for better chips, better technology, more and more every day. So what's the problem? Why are we thinking about quantum computing? What's the problem with how we make computers today? So one simple way to understand it is when we design and build computers right now, we actually take a piece of silicon and then we cut into it tiny little transistors, which are either on or off, which is how we encode our information, 1 or 0. So initially, we did this in a very kind of bulky way, but pretty rapidly we got down to being able to make chips where the features, the way that we're cutting these transistors in, that was on the order of 90 nanometers. And for those of you not familiar with nanometers, a nanometer is about 10 atoms, so very, very, very small. We got better and better at this, so as we were trying to make our computers better and better and better, we got better at cutting smaller and smaller features into that silicon, and that allows us to cram in more transistors, better processing, more compute. But there's a little trick that happens here. So you can see at 10 nanometers, eventually Intel says 7, 4, 3, they drop that nanometer. And that's because they are kind of cheating in the way that they're naming their future generations of processors. What happened is in 2011, actually a little while ago, we hit a limit. So we stopped being able to make smaller and smaller features in silicon. We can't cram more into the same space. We've had to start thinking of a lot of different ways of trying to build computers so that they perform better, but we've stopped being able to make things smaller. And the limit we ended up hitting was around 100 atoms. So this created a challenge. We want to make better computers, but we're at the level of individual atoms. So this was actually anticipated around 80 years ago by scientists who were just thinking about what could happen in the future. And that was the initial driver for why people thought about an idea of a quantum computer. They said to themselves, if I'm trying to make a computer, I'm cutting right now, but I'm going to hit a limit of around 100 atoms. What if I instead went the other way and tried to build a computer from individual atoms? And initially you might be like, that's crazy, how would you be able to do that? But this is an actual image. So here, that is an image that is in a lab today of 1,000 atoms which have been trapped in a grid where we can address every single one of them. So we really are now we've developed technology where we can engineer arrays of individual atoms. So a quantum computer at its simplest level can be thought of as building a computer from the bottom up with quantum things, atoms or other technologies. So trying this, it seems like initially a great idea, but it adds a complication. And that complication is that physics gets weird when it's quantum. I've got one more piece of experimental evidence. Again, forgive me, as a lecturer, I just had to put it in. So what is quantum? What does that mean? What does that intuitively change? So years ago, in I think like the early 80s, No, sorry, the 20s actually, this is way back. People were doing experiments with individual electrons. So we were trying to understand how the world worked us on the smaller scales. So what we did is we shot individual electrons through what's called a double slit experiment. So there's two slits here and a piece of a shield, and you're trying to let the electrons through. So if the electrons acted like bullets, like individual particles, you'd expect there to be these two lines that occur, just as if you're shooting. What happened instead is these images show a real experiment that was performed, and each dot was an electron, which was shot one at a time. So the experimentalists, what they did is they just sat there and waited, and over time, instead of seeing two big peaks, they actually saw up and down, up and down. They saw what looks like a wave on water. So we now understand the reason that occurred is because on the smaller scales, individual electrons, atoms, they don't act like particles, they act like waves. So they're not just in one position, they don't just go through one slit, they actually go through both. And so I'm just visualizing here, what you can think about is each electron looks like a wave going through those slits, which creates these two wave sources, and they interfere. And that interference is what gives you that up and down. So what does this have to do with computing? Well, in a traditional computer, you have things which are either 1 or 0. So they're in one slit or the other. In a quantum computer, because things on the smaller scales, like atoms, act like waves, they're actually in a combination of both. So you're not just looking at a single option at a time, you're actually looking at a combination of information when you're processing things on a quantum computer. So initially, that drive was, okay, things are a little bit different, things are waves on these scales, can we still compute? Very quickly, we discovered the answer is yes, but then something really unexpected happened. We discovered that it's actually, in many applications and many problems, it's actually better to use a quantum computer. That combination of the information being in both a 0 and 1 at the same time allows you to solve problems that would be almost impossible normally. And that opened a wave of applications. So it started with something a little more sinister. We initially discovered that if you currently today go and do a transaction with your bank, you can make sure that no one else is listening by something called encryption. One of the first things we discovered is that a quantum computer, if it was able to be built at scale, can crack that encryption and actually allow someone to listen in. So fortunately, there are other solutions that have come through to solve that, but you can see that's an example of how there is something special going on with these devices. And since then, we've discovered many other applications where using a quantum computer is better than a classical computer. Because of that drive, there has become a global race to find the right way of building a quantum computer out of the many options that are available. So atom computing was one, and that's where I took those images before. They were trying to build a quantum computer by arranging individual atoms trapped with light. There are two amazing companies in Australia doing fantastic work. One is Quantum Brilliance, who is using diamonds to create a new kind of quantum computer. And finally, Dirac is building on the infrastructure of silicon and trying to build a quantum computer on silicon itself. There are also many other competing platforms, from IonQ to trapping individual ions to PsiQuantum, who's looking at using photonics, light. Some of the best devices that are currently available today are what are called superconducting devices, and those are actually available online. You can use them at any time you want, not necessarily from Google, but from IBM. IBM has quantum computers available today, which you can use online. So what is our part to play in this space? What have we been doing? So at Q-CTRL, what we're working on is taking anyone who really wants to get into this space, allowing you to learn what a quantum computer is and upskill your workforce. We then have ways in which we can help you plan, discover how a quantum computer is going to be useful in your space. And then finally, where we really started and the meat of a lot of our development has been is we improve the performance of any quantum computer you want to use. So we make the execution better. So if you want to start, this is your best entry point into learning more about quantum. We have a product called Black Opal. It's available today. You can try it for free. It's an online sort of like Duolingo for quantum. So every day you've got exercises which teach you each of the pieces you need to understand to build a picture of what a quantum computer is and then what it is useful for. And it's available both for you to use on your own, or if you want to have it, you can give it to the rest of your employees or workforce to upskill them. We then work with specific partners who are really interested in finding applications of those quantum computers for their needs. So most of our partners in this space have typically been governments who are trying to better understand how to improve logistics and transport problems. So this has been something that we've really been leading the way in pushing forward for an application of a quantum computer that we think is going to be in the near term. The reason we think it's a good idea is not because it's big data. So sometimes people say big data, big quantum computing. That's not necessarily right. Big data means lots of compute, and there's just not a lot of quantum computers available to do that right now. Instead, what you should think about is quantum computers are typically really, really good at big problem space. So a classic example of this is a logistics or transport problem. So for instance, we've been working with the Australian Army to look at transport options. So you are trying to get things from A to B, and you're trying to sequence them in a particular order as efficiently as possible. So this ends up being an optimization problem when there's many different ways of configuring what routes you would take, what you would sequence first or last, or when you would go. That is a big problem space to occur, and what we're finding is that quantum computers are much more efficient at searching that space and finding the optimum, the best way for you to arrange your transport problem quicker than a regular computer. When we've been applying this to lots of different problems, whether it's optimization of rail networks, as in trying to get people from A to B more efficiently, or doing additional challenges like trying to route and improve the distribution of EV chargers, so like electric vehicle placement. So finally, once we've worked with a partner, when we've found that application where we're preparing them to embrace quantum computing for that particular task, our other technology is we actually improve the performance of that quantum computer itself. So we sit between, so IBM is one of our examples of a quantum computer that uses our software today, and we improve the quality, basically the probability that it gives you the right answer. And this can be as high as a factor of 1,000 for a lot of challenges that you would want to try and solve in these optimization problems. For those of you who are more technical, you're welcome to, we've got some papers which demonstrate this technology in action, and we actually did the world's largest optimization problem on a quantum computer to date. So I've talked about these applications, I've told you in the simplest way what a quantum computer is. Why isn't it here today? And that's a really important question. So there is a race going on because it's really, really hard. It's very difficult to engineer things on the atomic level. There's a lot of technical challenges and just like, how do you make something so small and cold? And then it's very difficult because it's very fragile. So given our experience, I've been doing this for 7 years and I've seen how the technology has progressed. We see in 3 years from now, that's when you're going to see quantum computers which are built and reliable enough to solve problems better than a classical computer, where you would choose the quantum computer. And those applications where we see that happening are, again, in this optimization space, but also chemistry. So quantum chemistry, it's called, but basically understanding chemical reactions involves a lot of quantum mechanics, a lot of quantum science, so it happens to be well suited to a quantum computer. Fortunately, some of the more scary applications, like breaking cryptography, look to be further away. They require a much higher quality, a lot larger device, and that is not looking possible for 10 years. But these are the kind of times you should be looking at as a business and determining when you want to engage. So if you're the type of business who's looking 3 years ahead, 4 years ahead, you do want to be thinking about quantum computing. You probably want to understand the impact it's going to have. But if you are currently just looking day to day, you can wait. You can wait a little bit, and you can try and catch up later on when the technology arrives and starts to make an impact. Thanks for your time. If you want to talk to me, you can check out the Ag app, where my details are there, or just use this link. Thanks very much.